Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last couple of classes, I was talking about organolithium, and then I talk about the organomagnesium or the Grignard reagent. And in the today's class, I'm going to start with the organocopper reagent. Then in the next class, I'm going to talk about the organozinc. So in the today's class, my plan is to talk about how what is the definition of organocopper reagent, and what is the structure going to look like. Then I am going to talk about the different type of reaction using organocopper reagent. So the discovery of organocopper reagent happened in 1859, okay, when Rudolf Christian Bodger actually discovered the cuprous acetylide. Okay, so that is the first organocopper compounds. Again, in the definition of organometallic compound, you know that there will be organic part and there will be a metal. So very similarly, there will be copper, which is attached with a R group, which could be a alkyl, aryl. Okay, so consists of a copper and a carbon bond. Again, I think that's not all. I think there are more different variations. Of course, you are going to see. So this is the compound. It was the early discovery about the copper acetylide. And although the copper have they adopt a different range of oxidation state from 0 to +4, but mostly you are going to see the organometallic chemistry of copper is mostly limited with the mostly associated with the +1 oxidation state. So let's start with the another earlier discovery. So you have seen that the earlier organocopper compound which was discovered, the cuprous acetylide. Now I'm going to talk about another discovery by Henry Gilman. So I think you guys are familiar with this reagent called Gilman reagent. I'm thinking you must heard about this reagent if you have learned the reagent chemistry. So now I'm going to talk about the discovery in 1936 when the Henry Gilman actually synthesized lithium dialkyl cuprate. So I'm talking about, first I talk about organocopper, now I'm talking about cuprate. So let's try to understand what is the difference here. So when you take a methyl lithium, add to copper iodide, that will generate the copper methyl. So this is an organocopper reagent, okay, as I mentioned in the previous slide, copper with R. But now once you use another equivalent of methyl lithium, then what is going to happen? It is forming a Me2CuLi. So this is called a cuprate reagent. So this is a dialkyl cuprate reagent, okay. So that is the discovery was done by the Henry Gilman. So once at the beginning when the organocopper reagent was started synthesizing, there was a lot of limitation, because organocopper reagent has a lot of issue like have a poor solubility, poor reactivity, and also thermal instability. But once you think about this cuprate reagent, the Gilman reagent or the cuprate reagent actually relatively more soluble compared to the copper reagent, and then they are thermally stable, and the most important thing is they are even more reactive compared to the organocopper reagent, okay. So here are the structures. So this is a dimeric form of lithium dimethyl cuprate in a solution, and this is also a dimeric form of lithium diphenyl cuprate in a solid state. Again these are going to confirm from X-ray crystallography these compounds in the solid state. So now we are going to learn about some of the different type of organocopper reagent. Okay, so we have learned about the organocopper and the cuprate. Now you can think in the cuprate there are these three important class we need to consider. One is the neutral homoleptic organocopper cuprate, as initially discovered by Gilman. You can see these are homoleptic because there is one donating ligand attached. If there is two different, then we are called them heteroleptic. I am going to come back to that. So the first thing is this neutral homoleptic organocuprate, okay. And then there are ionic species. We are going to talk about some of these, often by strongly coordinating molecular species like crown ether. Then there are heteroleptic cuprates. I am going to talk about there will be different ligand bound with the copper, okay. So I am going to talk about some of the heteroleptic cuprates, and you will see there are sometimes there will be one particular group, there will be two different group, and one particular group going to participate in a reaction, okay. I am going to talk about all these different things. So before I go to again, and I think before I discuss any of this organometallic reagent, always I talk about the reactivity of that reagent compared to the organolithium or Grignard. So one of the important thing is the difference in electronegativity. You must have heard in the previous time when I was discussing organolithium or Grignard, that is one of the important factor, and that decides the polarity of the bonds, okay. So you can see here the difference here is very high in case of lithium, it is going down in this direction. As you can see here, once you go in this direction, the polarity getting decreased as the electronegativity difference is getting decreased, the polarity getting decreased. At the same time, there is another thing getting decreased, which is the percentage of ionic character. That is also getting decreased once you go from lithium to magnesium to copper. As the percentage of ionic character is getting decreased, these compounds are becoming more covalent. Okay. Again, you can see the another important thing is I think I have mostly talked about that you will see the copper the organocopper reagent, you will find mostly +1 oxidation state of copper, and then you will see there will be less pi back bonding due to achieve its higher oxidation state. Okay. So you can see that the organocopper is much less reactive compared to organolithium. So these are kind of a softer region, you can say. So these are some of the properties of copper region. One of the properties that the alkyl complexes are thermally unstable. I have mentioned at the beginning that the organocopper complexes are unstable, and it decomposes below 0 degree Celsius, and sometimes it can even explode. Again, these are the order of thermal stability of organocopper compound. Again, you can see the alkynyl is more stable than alkenyl, then aryl, then alkyl. You can see these are very similar trends you have seen when I talk about the carbon stability, correct? So that is the order it is following. Because of the the S character is very high in case of alkenyl, it is getting decreased to alkenyl, and it is even getting decreased in case of alkyl. So this is the example of a alkyl copper complex which is actually stable, because here the thing is when the alkyl copper complex is getting decomposed, then one of the thing is one of the mechanism is it is going through the beta hydride elimination process. So now in this type of compound, the beta hydrogen elimination is stopped, and because it does not contain a beta hydrogen, so that's why this compound was well characterized. It's a well characterized alkyl copper complex. So as I mentioned, I'm going to talk about the different type of organocopper reagent. First, I'm going to talk talk about the homocuprate reagents. Okay. So again, I mentioned about this in the definition of the homo and the hetero, correct? They are prepared by the reaction of copper bromide and copper iodide with 2 equivalent of organometallic reagent, which you have seen at the beginning when I started talking about the cuprates. So that means it is the first equivalent from the organocopper, which you can see here, and then the second equivalent kind of react with that to form the corresponding cuprates. Again, as I mentioned, the organocoppers are not always soluble. Okay, they are insoluble in some of the cases, but once you make to the corresponding cuprates, they are soluble. Here you can see you can have a transmetallation, means corresponding organolithium and corresponding copper bromide can form this corresponding dialkyl copper compounds. I mentioned you can do it first one equivalent, then another equivalent to form this type of cuprate, dialkyl cuprate. Then there are heterocuprate reagents. So you can see now you have two different groups here. You can see the copper bromide having the SMA2, and then you have also R2N. Okay. So that means you have an R2N which can so this copper complex now react with R1 lithium to form this type of like heterocuprate reagent, where you have the nitrogen and you have R1. Okay. So two different type of ligand is attached there. So you can see there are some of the variation here of the synthesis of the heterocuprate, which is I think one of the popular one is with this thionyl one. So it's a 2 thiophenol lithium with the RLI, and in place of copper iodide it is going to form this heterocuprate reagent. Again, there is another example here as well, and I am going to talk about some of the reactivity of this reagent as well. Then we are going to talk about some of the lower order cyanocuprate reagents. So that is another important thing, that depending on what type of you have copper iodide, copper bromide I talked about before. Now I am going to talk about copper cyanide. And once again the copper cyanide can be also reacted with the RLI to form this RCuC and lithium. These are the lower order cyanocuprate reagents. But once you add a 2 equivalent of it with the copper cyanide, then you end up making the corresponding cuprate, as I said. So this is a very important reagent. It's a higher order cyanocuprate reagent. Okay. So this is called Lifshitz reagent, and after this discovery, this complex this type of copper organocopper compound used for several default transformations. Not only by the the Lifshitz group, there are several other groups also have developed organic transformation using this Lifshitz reagent. So one of the important fact is this is much more reactive compared to the other copper reagent. Okay, and it has better thermal stability. So we are going to see for some reaction where you see the other organocopper didn't work, but you can see using the Lifshitz reagent we can see the transformation is happening. So now we are going to move to the different chemistry which was done with organocopper reagent. I think this is the most important part for for you, because you are going to see a lot of type of questions in the exam comes from mostly from the reactions of the organocoppers. First thing is we are going to start with the substitution reaction. That means the question comes now, if you make organocopper, can it participate in some sort of SN2 reactions? So now what is happening, you can see here it can participate in SN2 reactions. If you talk about this cuprate and take this corresponding alkyl halides, it is going to participate in a SN2 reaction. So there could be two different type of mechanism. One could be like a SN2 mechanism, or one could be some sort of oxidative addition going to happen. So this CX and this organocopper, so the copper going to go for oxidative addition to go from copper 1 to copper 3 here, and then it will be going for the reactive elimination to get back the copper 1 and the product. Okay. So here we are talking about the substitution reaction using the homocuprate reagent. So you are see the very similar thing happening. You have this corresponding Grignard reagent, you use copper iodide and the alkyl iodide. Now what is going to happen? The Grignard reagent is going to go for a transmetallation with the copper iodide to form the corresponding cuprate, and now it is going to react with corresponding alkyl iodide to get to the corresponding product. So this is the homocuprate reaction. And then you have seen the mechanism here, it's reacting with the copper iodide to form this corresponding homocuprate. Now it is going for SN2 reactions, or it can go for the oxidative addition and the reactive elimination to get to the corresponding product. So one of the important thing is this homocuprate always participate in a SN2 reaction or substitution reaction with a primary iodides. Okay. So now if you bring a secondary iodide, what is going to happen? The homocuprate actually is not very good with the secondary. So for at least for if you go for secondary bromide, you will not see much reactivity there, or in case of secondary iodide also. So that's why the heterocuprates are very good on that regard. If you have a heterocuprates, then what is going to happen in the heterocuprates, one of the groups, the methyl one, which is going to participate in the reactions, for the SN2 reactions. Okay, so in the heterocuprate there will be two different groups, and one will be the more coordinating with the copper, and then the other one going to participate in the reaction. Here this R group going to take part in the reaction to after the SN2 reaction, it will form this product. Again, there is now the question comes, once you have this corresponding bromide, now this homocuprate or this heterocuprate does not work for this reaction. Now you have to take this help of this Lipschitz reagent. As I was telling you, the Lipschitz reagent is much more reactive compared to this homo or this heterocuprate. So now Lipschitz reagent can participate in this reaction here, this substitution reaction to form the product. Okay. So now if you can understand what is the importance of Lipschitz reagent. One of the important facts about the substitution reaction, what was find out that once you have a X equal to iodo, if it is a secondary iodide in place of a cuprate, it is the racemization which is happening here. So this stereocenter, which if you start with the chiral compounds, here the chiral halide, you end up getting a racemized product. Okay. So you will end up getting a racemized product here. But once you have a bromo here, once you have a bromo or the OTS, in that case there is a inversion happening, very similar to a SN2 reaction. You are seeing an inversion happening, and you see the stereochemistry. If you start with S, you end up getting to the R. Okay. Again, now we are trying to understand some of the evidence that if you have a secondary, suppose you have an iodo here, X equal to iodo in this particular substrate, instead of forming the desired product, it is also forming another important compound, which is this one. Okay. So you can see here you kind of getting up to 65% here when the I equal to iodo. So what is happening here? Now you can understand that if I equal to iodo, then there is a formation of a radical. So once you have this radical, now you can see if you give them a 1, 2, 3, 4, 5, 6. Again we have learned about that if there is a radical formation happen, the radical can participate in a 5-exotric. Okay, that can end up giving to this product. So that is kind of justifying that yes, it's going through radical intermediate. Now substitution of allylic substrate. I think this is a very important topic. So what is happening if you have allylic acetate here, and if you treat with the Grignard reagent, okay, if you have a Grignard reagent at the, with a 2 mole % of this corresponding copper salt, what is going to happen? It is going to form. Now if you have two different addition here, one is fast addition, that means you add them first over 4 minutes, that means you take your substrate, you take this organocopper and you are adding Grignard into the reaction. Now, if you add the Grignard in over a 4 minute, that is means in a very fast addition, you end up getting to the majorly to the SN2 product. So, there is a two possibility. It can either go for a SN2 like directly attacking here, or it can go for a SN2 dashed. Okay. So, now this is happening that once the addition is happening slow, that means you are adding this butyl, magnesium, bromide over 30 hours. Okay. What is happening here, once you adding for a longer time, you are getting majorly to the SN2 dashed, okay, and then minor is the SN2. So, this is just a single scenario, but you see this type of allylic substrate SN2 versus SN2 dashed is depend on not only the addition, it depends on the temperature, it is also depend on the substrates, okay, and also the Grignard reagent. Okay. So, there are well studies was done, everything was published about that. So, now what is happening, the author of this publication has actually reported that when you are doing a fast addition and a slow addition, they think that in case of fast addition it is forming some sort of a copper organocopper species which is going for a SN2, and here when you go for slow addition, it is forming a cuprate. It is forming a cuprate with 100% formation of cuprate, that is allowing for the SN2 dashed reaction. So, that means they are saying if you have a cuprate, then that is going for SN2 dashed majorly. That is why you are getting as a major product here. We are trying to understand what is happening here. So, you can see here, if you think about this particular compound, this allylic halide or allylic acetate, you can think about, so we are talking about the pi star is interacting with the, so there is the d orbital of the copper. So, the d orbital is copper actually interacting with the pi star of this double bond and the sigma star of this carbon halogen or the carbon OS, whatever the bond is. So, it is a simultaneous d pi star and d sigma star interaction is happening, okay, in the transition state. Okay. From there it is oxidative addition happening, copper is going to the copper 3, and from there it is forming this allylic complex, and then it can go for SN2 or it can go for a SN2 dashed. So, it can from this, it can give two different copper 3 species. After that it is going for the reactive elimination to form the two different products. Okay. It can either go for SN2 product or it can go for the SN2 dashed. Okay. Again, in this reaction, I think I did not put the example here, but you can clearly understand if it is going through this type of copper pi allylic species. Now, if you have a chiral ligand attached here, if you have a L here which is chiral attached with the copper, then that can also control the enantiomer selectivity in this reaction. You can end up getting to the chiral product using a chiral ligand. The other important reaction is the epoxide cleavage reaction. You can see, if you use a cuprate, it is going to attack to the less hinder position here in the of the epoxide to form this corresponding tertiary alcohol. Okay. And you can see substitution takes place with complete inversion of the configuration. Here you can see in this particular cases, this is a allylic epoxide. Okay. In case of allylic epoxide, once you are using a cuprate, as I said, in case of cuprate, you will observe that it is going for majorly to the SN2 dashed. Okay. So, you will see the major product will go from attacking here. Okay. It is shown in this corresponding transition state, and you can see there here it is, if you try to draw them, you can see this is the position where the nucleophile can approach, okay, to form this corresponding product. Another example of the epoxide cleavage, again as I said, if you use this copper with a thiophene, then that is not going to get migrated. The other the nucleophile or the R group which you are going to add to the copper, that is going to form this dianionic complex. Okay. Once you form this dianionic complex, this corresponding cuprate that can take part reaction with the epoxide, again it is going to attack from the less hindered phase of the epoxide, okay, to form the product. Then reaction with the vinyl halide can also react with this corresponding cuprate. So, there is sp2 hybridized, but still the reaction is happening with the copper. Again you can see that it can go through this type of oxidative addition and a reactive elimination to introduce this N-butyl group with high stereoselectivity. Another very important thing, I think, if we talk about organocopper, then I think this is the important reaction. We always talk about the use of Gilman reagent for this 1,4 addition reaction. So you have learned that if you have this enone type of compound, have a carbonyl group and a double bond. Now if you have a nucleophile, there is a two possibility. One is the 1,2 addition, another is 1,4 addition. So it can attack here, then it is a 1,4 addition, and if it is attack here, this is 1,4 addition. So sorry, that is in the 1,2 addition. Now that is, you have seen, if you have a very very hard like organometallic compound like organolithiums or for the Grignard, where you have seen that mostly it is the 1,2 addition is the preferable one. And this is a hard center, that's why these reagents are going to attack in here. But if you see about organocopper reagent, these are soft reagents. So you can see now this is the soft center. So now nucleophile is, if you have a organocopper species, it will going to attack here to go for a 1,4 addition. Okay. So we try to understand the mechanism of this reaction. Once you have this cuprate, then there is a first formation is this copper olefin pi complex formation is happening here, which again involve the d pi star back donation. Okay. And once the pi complex formation is happening, from there that could be one possibility, could be a carbocupration happening here. It introduced the methyl already here, the methyl transfer from this place to this carbon, okay, to form this carbocupration product, carbocupration intermediate, or it can go for this copper 3 intermediate species here. Okay. Here it can go for a like you can see here, it is first going for a copper 3 species here, after that like some sort of oxidative addition happening here to go to the copper 3, and then from there is a reductive elimination is happening, giving the methyl back here to form this type of, so it is going to form a enol, from there it is going to form the pi adduct of the copper and the double bond of this enol, and then finally it is going to form the product. Okay, you can have this type of enol, and then once you have a H3O plus, it is going to form the corresponding product here. Okay. So now the question comes, of course there will be stereochemistry will be important. Now if you have a compound here, or you have a CH3 groups, in this type of cyclohexenone, you have a CH3 groups in the 4 position. So now the question comes, once this nucleophile going to attack, what will be the attacking? It will going to be attacked from the up or the down, because there will be two possibility. Either the product could be anti, which is here, or it could be a syn. Now that can be explained from the corresponding tangent state. If you look into the corresponding transition, the allele 1,2 strain is going to be one dictating factor, which is going to happen if the R is approaching from this side, from the same face of the methyl group. Okay. But in the other cases, if the methyl is not here, the methyl is on the other face, then the R can clearly approach from here to form the corresponding product. That's why we end up getting to the the anti product as a major product. The beta disubstituted ions less favorable with organocuprate due to the steric crowding. So again, if you have a disubstituted groups here in the position where the nucleophile going to be attacked, the organocopper going to be attacked, then there are less favorable. In that cases, you have to use a Lewis acid. So BF3 etherate is a very common Lewis acid to activate this oxygen. So you have this BF3, the boron is actually a Lewis acid which can take the electron density from the oxygen, make it more activated, decrease the homolumo gap, so that nucleophile now can able to attack here to form the corresponding product. Again, there is another example here, using this vinyl cuprate, it can add here to get to the corresponding product with a quaternary stereocenter here. Again, there are there are substrate where there is two different position can be attacked. One, it can attack from the this side, which will be less hindered, compared to this side, which will be the more hindered. Correct. So you can see the nucleophile is attacking from the less hindered side, which is this side, and also it is attacking to the opposite side of this methyl. If the methyl is up, this methyl is approaching from the other face. It is shown here in the mechanism. Okay, and after that, once you take H3O plus, it is going to get to the corresponding product. So now we are going to talk about, we have learned about this 1,4 addition, but what about, we have learned that in the 1,4 addition, we are always making this type of enolate. Okay, because you can see we have this R2Cu Li, and you can see the lithium always kind of bound here in this with the oxygen, so to form this type of enolate species. Now if you have this enolate species, now if you give a electrophile, then you can trap this enolate with a electrophile that can give you simultaneously formation of two different bonds. one it could be, so first thing is this is this is one for addition, and now this is a enolate trapping. So that means you can able to form these two bonds here. Now this trapping could be with a carbon, that means once you have this enolate can be trapped in the carbon, or it can able to trap with the oxygen. Means if you use something like silicon and all this like tin, then that can go to the oxygen. And if you have some sort of a alkyl halide, then of course there you can see again that this hard soft concept again comes into the picture. So this carbons, this is a softer place, so it can take with a carbon based electrophile, then you will see the substitution here. Okay. So that's why the carbon trapping, we are going to show you some of the example here. As I mentioned here, if you treat with this N-butyl Cu2 Li, so this Q period going to go for 1,4 addition, and then what is going to happen once the 1,4 addition is happening, you can understand from this tangent state that after the 1,4 addition is happening, now this enolate is going to take the electrophile in the opposite side, opposite face of the butyl group, because again to avoid this steric interaction you have seen there. So that's why it is going to take the methyl iodide in this phase to end up forming this product as a major product. Okay. Again there is an example here. First there is 1,4 addition, then you take take this allyl bromide, which can go for a which can attack to this, form this allyl product here with the anti product as a major product here. Okay. So you can introduce a vinyl in this position and the allyl in the next position. Okay. So in a one particular shot you can actually first add the copper reagent, and then at the end of the reaction you can add the electrophile, continue the reaction, that can completely consume the electrophile to give it to this product. There is another example here. I think here the reaction is happening in a intramolecular. First thing is of course you add the methyl, this methyl going to attack here. So this is the 1,4 addition first going to happen. Okay, and then after that this enolate going to form, it is going to attack the corresponding alkyl halide to form this corresponding bicyclic compound. Now as I said, if you have this trimethylsilyl chloride, then again these are going to favor with oxygen. We know about that. Again this hard soft concept come to the picture. So this is going to bind with the oxygen to form this OTMS. Okay. So after this step, instead of attacking the carbon, it is going to take and form the corresponding OTMS. Of course, if you get this corresponding OTMS, this compound can again you can treat with a electrophile. Okay. So now I am going to talk about the asymmetric conjugate addition reaction. So we have learned about the conjugate addition reaction. Now the question comes that in this conjugate addition reaction in the copper, if you can bring a chiral ligand, then you can able to control the chirality, and you can able to make product where you have a particular enantiomer selectivity. That means it could be R or S. Okay. You can able to control them using a Josephus ligand. So that was the early ligand Feringer group has developed, and they try to study the mechanism. So again I think what the understanding from these particular things, they try to do the mechanistic understanding for this type of asymmetric conjugate addition reaction. What they find out once they treat with this corresponding copper halides, they found that it is forming some sort of a dimeric species here with a halide bridge with the copper here. Okay. So and then it's going to take part. So they actually mentioned that it is forming first this, and then it is forming also this one. Okay. So it is kind of in a equilibrium. So this this one and this one in the equilibrium. And then what is happening again, the reaction is reaction mechanism is very similar, that once you have this RMGBr, it now able to generate this corresponding copper species, which is going to now take part into the 1,4 addition reaction. Again the magnesium Br actually going to activate to forming this pi complex. As I mentioned in the 1,4 addition mechanism, the formation of pi complex is the first step. Here this MgBr actually acting as a Lewis acid to activate this oxygen. Now this it can go for this oxidative addition to go to this copper 3 species, and then reactive elimination to the corresponding product. Again there are some example here using this type of Josephus ligands, you can get to the now this product with high enantiomer selectivity. So in the previous slide we have learned about this 1,4 addition. Now you can see in this particular cases, if you have a enone and then if it is conjugated, that means there is another double bond here, then you see there is this 1,6 addition is getting predominant. So you will see this 1,6 addition is happening, and then you of course get some little amount of 1,4 addition, but the major will be the 1,6 addition product. Okay. So that you have to be understanding that if you find there is a enone, and again you can see this is a this position is also getting hindered. Okay, so this is also a tri-substituted. You have actually both the substitution here. So in this double bond is actually a disubstituted. So this is going to form a quaternary carbon. So sometime if you have a conjugation, then it is preferred for 1,6 addition. The other important reaction is the carbocupression reaction. So if you treat with a Grignard reagent with a copper bromide, then you end up a carbocupression reaction by forming this species here. So you have this C6H3 Mg Br with copper Br. It is forming this the RCuMe2S MgBr2. So I think I talk about a lot about this RLi, correct? I talk about the organolithium and the copper. Now here I am talking about the magnesium. So once you take organomagnesium, and then if you have alkyne, then it can go for a carbocupression. I think I mentioned the carbocupression in once I talking about the mechanism previously there. So after the carbocupression, what is happening? Both the copper and the alkyl group add to the alkyne in a syn addition, okay, to form this. And once you have this vinyl copper species, now you can, if you have this enone, cyclohexenone, it can go for 1,4 addition here comfortably to get to this product. Another type of reaction I should also mention is called acylation reaction. If you have a acyl chloride, now you have learned that if you treat with the organolithium or Grignard, what is happen, correct? It is going to attack to the corresponding ketone, and it is not going to stop there. This ketone is going to get attack again. But if you have this organocopper reagent, then there is advantage here. Using organocopper, you can able to introduce the alkyl group comfortably to form the ketone, and this is not going to attack again with the organocopper. Okay, so that is a very important thing. So there is a chemoselectivity here. You can see here there is an example here. This corresponding acid chloride in place of Me2Culi is introducing the methyl group here. You can think about if you take methyl lithium or methyl magnesium, methyl magnesium bromide, you will not able to get to this product. And the other important thing is in this slide I should mention there is a ester versus acid chloride. I think this is a very important. So there is an important chemoselectivity here all. You are seeing that the reaction is only happening to the corresponding acid chloride to get to this ketone. Is kind of this ester remain untouched, which will be difficult using a Grignard or corresponding lithium. The final slide I am going to talk about a Sonogashira coupling. So this is again a very important cross coupling reaction. What is happening in this cross coupling? You have this aryl halide. Okay, it could be a bromide or a bromide or a iodide, and then you have alkyne. So now what is happened, once you know that if you use a palladium catalyst, we have previously learned that if you have a aryl halide with a aryl bromide or iodide, mostly you will find that is going to participate in oxidative addition to form palladium. Okay, so palladium is getting oxidized to palladium 2, correct, from palladium 0. So we have learned about that, and we have learned about in the Kumada coupling that if you have a Grignard reagent, that is going to transmetal it, correct, and then it is going for reductive elimination to form bonds, and then you have seen that. Here you have a alkyne, and in presence of base and copper iodide, catalytic amount of copper iodide, what is happening here? The copper is forming a corresponding copper acetylide. Now here this copper acetylide is going to participate in a transmetallation. So in this transmetallation event, you see again palladium will be palladium 2, but you now have alkyne group here. Okay, and now it is going to go for a reductive elimination to form this alkyne. So now you convert this R to, so this is the product, you have this Ar, so that will be the final product here. Okay, and there are some example here. If you have a compound with this aryl iodide, and if you take this corresponding acetylene, TMS corresponding TMS, not TMS, it's a tri isopropyl silyl group here, and there is a alkyne here. If you take the palladium catalyst, copper iodide, triethylamine, this is a very common condition for Sonogashira coupling. What is going to happen? You introduce this alkyne here, you replace this iodine and introduce the alkyne, which can further transform to a bioactive compounds. Here if you can see another example, you have aryl iodide here, palladium catalyst, ligand and copper, and in place of this base, it is going to introduce again, replace the copper iodide, replace the corresponding iodo and replace the alkyne, which is going to form these corresponding natural products. Again, I hope you have convinced that the organocopper chemistry is very powerful chemistry. There are a lot of different type of carbon-carbon bond formation can happen using organocopper chemistry. Here are some of the reference books you can study. And again, thank you so much for coming to the class, and I am going to see you guys in the next class. Thank you.